My cousin Nadia is taking a summer calculus course, and she called me last night, and she had some limit problems, and they were excellent problems, so I thought it was worthwhile to make videos on the problems that she had to figure out. Anyway, so let's do them. If I remember them correctly, I'm doing this on memory, so I hope the answers work out like they did last night when we were going over them on the phone. So if I remember correctly, the first problem was the limit as z approaches 2 of x, oh no, not there, why there's no x, it's a z of z squared plus 2z minus 8, all of that over z to the fourth minus 16. So the first thing when you want to do when you try a limit problem is, well, you just try to substitute the value into, maybe there's no problem when z equals 2, and you just evaluate the function at z equals 2. If it's a continuous function, then the limit as it approaches 2 is going to be the function at 2. But you immediately see a problem. If you put 2 right here, 2 to the fourth minus 16, you get a 0 in the denominator, which is undefined. So we have to figure out some way to get around that. And 9 times out of 10, when you see a problem like this, the solution, because both the numerator and denominator look factorable, is to factor the numerator and the denominator. So this is equal to the limit as z approaches 2. What's the numerator factored? Let's see. When you add two numbers, you get positive 2, and you multiply them, you get minus 8. So it's probably plus 4 and minus 2. Right? So this is going to be x plus, no, not an x. I'm so conditioned. I'm like a dog. Oh, I can't even undo it anymore. Anyway, well, z, actually, I'm going to erase that. I don't want to be messy. Let me erase. I tried to undo it, and it doesn't remember everything. So it's z, let's say, plus 4 times z minus 2. That's just factoring a quadratic. And what is this? This has the form a squared minus b squared, right? So that's going to be, but a squared, and if this is a squared minus b squared, a would be z squared, right? So it's z squared plus 4 times z squared minus 4. And then, of course, this also has the form a squared plus b squared, right? So this will further factor into z plus 2 times z minus 2. Well, our factoring paid off. We see a term in the numerator and the denominator that are the same. And not only are they the same, but this is the term that was giving us the problems, right? Because when you put a 2 in here, you got a 0. So let's assume that we're not evaluating at z equals 2. And so for all other values, we can divide those, because those are going to be the same values. And then what are we left with? This is equal to the limit, and I've changed colors arbitrarily, as z approaches 2 of z plus 4 over z squared plus 4 times z plus 2, which is equal what? That's equal to 6 over, what's 2 squared plus 4 is 8. And then 2 plus 2 is 4. 6 over 12 is equal to 1/2. There you go. I thought that was a pretty interesting problem. Let's do another one. And this one I found even more interesting that she gave me. It's really testing my memory to see if I can. But I remember the gist of the problem, so I might not get the exact numbers she'd given me, but hopefully I get the exact properties. So it was the limit as x approaches infinity of the square root, and this, see, the square root of x squared plus 4x plus 1 minus x. So when you look at this, you're like, well, let's see what's happening here. Let's see this. As you go to infinity, this term will get really big, but then we're taking the square root of it, and it seems like this term would overpower this term, and then so maybe this kind of converges to x, but then we would subtract an x, so maybe it approaches 0. So that's, at least, that was my first intuition when I spoke to her. But as we will see, the intuition here is wrong. And really, to do this, you have to know a little bit of a trick. And this trick pays off a lot whenever you see something with a square root sign and then subtracting something else, if you want to get rid of that square root sign. So what we are going to do is going to multiply. Essentially, the conjugate we normally apply to complex numbers, but if we have something like a plus b, the conjugate is a minus b, right? Or if we have something like a minus b, the conjugate is a plus b. And the reason why, and what we're going to do is we're going to multiply by the conjugate of this. And why is that normal? Why is that useful? Because we have a minus b. If we multiply it times a plus b, we get a squared minus b squared, which will make this radical sign disappear without too much work. So let's do that. Let's multiply by the conjugate of this thing. But we can't just multiply it, right? We have to multiply it by it over itself, because you can only, to not change the value of something, you can only multiply by 1. So let's multiply it by the conjugate, x squared plus 4x plus 1 plus x, right? That's the conjugate, right? Instead of minus x, we have a plus x. And we can't just multiply that. We have to multiply by 1. Otherwise, we would be changing the value. So it's going to be divided by the same thing. X squared plus 4x plus 1 plus x. Let me erase this stuff down here so we don't get distracted. Don't want to get distracted. And so what do we have? This will become the limit as x approaches infinity. Well, this is a minus b times a plus b, so we end up with a squared. Well, what's this squared? That's x squared plus 4x plus 1 minus b squared. Well, what's b squared? B is x, so it's going to be minus x squared. And this is just algebra. Divided by this thing, the square root of x squared plus 4x plus 1 plus x. So let's see, there's a little simplification we can do. We can subtract, these top two terms cancel out. So x squared minus x squared. And now let's see what we can do. Well, since we're taking x to infinity, and this is what you normally do when you take x to infinity, we can divide the numerator and the denominator by our highest degree term. And in this case, our highest degree term is x, right? We have an x here and an x here. And then of course when you divide something like this by x and you take to infinity, this will approach 0. So let's do that. Let's divide the numerator and the denominator by x. And remember, anything you do to the numerator, you have to do the denominator. Otherwise, you're changing the value. So times 1 over x over 1 over x. I'm just dividing the numerator and the denominator by x. So this is equal to the limit as x approaches infinity. That's going to be 4 plus 1 over x over. Let me ask a question. What is 1 over x times this thing? What is, and this is a bit of an algebra review, but 1 over x, what's 1 over x times, x squared plus 4x plus 1? I'm just doing a little aside here. Well, if we take the 1 over x and we put it into the radical sign, it becomes 1 over x squared, right? This is the same thing as, you could say 1 squared over x squared, but, 1 over x squared. You could say 1 squared, you could put a squared there, but times x squared plus 4x plus 1. And that should make sense to you, right? Because if we started with this, we could easily just take the square root of this and take it outside. And the square root of this is 1 over x. So I'm just going in the other direction, right? So, assuming you're comfortable with that, everything under the radical sign, even though we're actually dividing by 1 over x, since we're going into the radical sign, we're actually dividing by x squared. So it becomes, this is the radical sign, x squared divided by x squared is 1. Right? I hope you understand why we're dividing by x squared here. We're actually dividing by 1 over x, but when you put it on the radical sign, it becomes 1 over x squared. Let me put it this way. 1 over x times the square root of a, that's the same thing. That equals the square root of 1 squared over x squared times a, right? And this is just 1 over x squared. So that's the property or the algebra that we're using. So anyway, we divide all of this by x squared. So that becomes a 1 plus 4 over x, right? Plus 1 over x squared. And then, of course, we divide this one by this term right here. We divide by x, right? Because it's not in the radical sign. So that just becomes a 1. So now, what's the limit as x approaches infinity? Well, as x approaches infinity, this term right here goes to 0, right? 1 over infinity is 0. This term right here goes to 0. This term right here goes to 0. And so what are we left with? This is equal to 4 over, see, the square root of 1 plus 1. Well, that's just 1. So that equals 4 over 2, which is equal to 2. There you go. Now, let's do one more problem. This is the third one she'd given me, and we had to kind of brush off our trig identities. And really, these harder limit problems, they're all about kind of knowing your algebra and your trigonometry really well, just so you know how to manipulate these functions. Because the limit part, you just have to get into a form where taking the limit is fairly straightforward. So let's do that trig problem. Clear image, invert colors. So it was the limit as x approaches 0 of cotangent of 2x. Was that it? Yeah, it was cotangent of 2x over the cosecant of x. And this one, just like previous problems, more than knowing your pre-calculus or your calculus, you need to know your trig identities. So cosecant of x, that's just 1 over sine. I remember that by saying it's non-intuitive. You would have thought that cosecant is 1 over cosine, but it's not. It's 1 over sine. So I remember that it's non-intuitive. And cotangent of 2x is equal to 1 over tangent of 2x. And tangent is sine over cosine, so cotangent is the opposite. So that equals cosine of 2x over sine of 2x. Right? Okay. So what is this equal to? So this is going to be the limit as x approaches 0. Cotangent of 2x, we said, was cosine of 2x over sine of 2x. And then it's going to be all of that over the cosecant of x. Well, that's just 1 over sine of x. 1 over sine of x. Well, if you divide by 1 over sine of x, that's the same thing as multiplying by sine of x. So we have, what do we have? We have cosine, well, we have sine of x times cosine of 2x. All of that divided by sine of 2x. Just doing a little arithmetic. And we have a problem here still, because when you take x approaches 0, this term right here goes to 0, and we have a 0 in the denominator, which is just not acceptable because it's undefined. And that's the whole reason why we're doing this limit to begin with. And actually, that's the first thing you should have done. You should have tried to put it, and you would have seen that you would have gotten a 0 value in a denominator, and it would have been unevaluatable. Right? Because really, this is just, we haven't even done any manipulation yet. This is the same thing as this. And if you put the 0 right here, you get undefined. So what can we do? Well, this is where you break out the trig, or you brush off your memories. What is the sine of 2x equal? And this is your one of the double angle formulas. Sine of 2x, it is equal to 2 sine of x cosine of x. So if you know that, then you've gone a long way, because then it becomes pretty simple to simplify. So it becomes 2 sine of x cosine of x. And then if we assume that x isn't 0, it's just approaching 0, we can divide the numerator and the denominator by sine of x. And what are we left with? We're left with the limit as x approaches 0 of cosine of 2x over 2 cosine of x. Well, what's cosine of 0? Cosine of 0 is 1, right? So cosine of 2 times 0, which is 0, that's also 1. So that is equal to 1 over, right, cosine of 0 is 1 over 2 times 1. So it equals 1/2. There you go. I think those are 3 fairly meaty limit problems, and if you know that, you're probably prepared for something that your calculus teacher might throw at you. See you in a future video.